So I'm going to do one last example of a related rates question with you, and I like this one because it involves some trigonometry. So I've got a beach, and I know it's looking like a very artificial beach because it's a very straight beach. So here's all the sand here, and I'm going to have a lighthouse out in the water here. So here's my lighthouse, and my lighthouse has got a light on it that's sweeping round and round, and the light is going at 1 revolution every 15 seconds. So my question is, how fast is the light sweeping across the beach? And that depends on where you're standing at the beach. So I want to find out how fast is it sweeping along the beach, when you are 400 meters away from the closest point. So I need to know the distance between the lighthouse and the beach, which I've labeled here as 200. So that's fixed, and I've got that on my diagram. I'm also going to put a variable on here, which I've already have, my x. It's changing. That's where the light is at a particular time. So that is changing. And I've got z changing as well. But I need to find a relationship between these variables, and I could use Pythagoras. That would relate x and z and 200. And the important thing is to maybe focus on what I'm given. I'm given information about revolutions per second, really. So that's how fast is the angle changing. So I'm not going to use z at all. I'm going to use theta and say, okay, what's the relationship between x, 200, and theta? Well, my relationship is a tan ratio. The tan ratio of theta is the opposite, which is x, over the hypotenuse, which is 200. And I'm going to multiply both sides 200 to avoid fractions. So I've got a relationship here for x. And my question is, how fast is dx dt changing when x is 400? So there's my question. My information is given as a rotation information here. So my angle is changing. How fast is it changing? It's swinging through 2 pi, which is the full circle in terms of radians, every 15 seconds. So there's my rate for the angle. And now I need to, in order to use this information, I've got to take the derivative. So the derivative of this expression is 200, and then the derivative of tan is secant squared theta d theta by dt. It's been a long time since we've done some trig derivatives. On the right side, the derivative of x with respect to time is dx by dt. And now I'm going to plug in the values that I know. So I know that d theta by dt is 2 pi over 15. And I have an unknown of theta. Well, I know when x is 400, I can calculate theta using this relationship right here. So let me do that. So tan of theta equals 400 over 200. So the tan of theta is 4 over 2. And I could go inverse tan and get a decimal approximation, but what I want to know is what's the secant. So let me just insert a new page here to show you how I would do that. So in the instant in time where this is 4, I know this is 2, this is theta, then I could use Pythagoras to figure out what z is, which is going to be 16 plus 4, or the square root of 20, and more simplified, to square root is 4 times 5, so it's 2 root 5. And that means that the secant of theta is equal to, the secant is reciprocal of cosine, so it's hypotenuse over adjacent. So the hypotenuse is 2 root 5 over the adjacent, which is 2. So the secant is root 5. So let me go back now to the diagram that I've just done, and I'm evaluating this here. So the 200 I'm running out of room here. 200. The secant was root 5. We've just calculated that, and it's squared because of this square right here, times d theta by dt, which we know is 2 pi over 15. And that equals dx by dt. So now it's just a matter of simplifying that. And let me do that on a new page. So we have dx by dt was 200 times root 5 squared times 2 pi over 15. So root 5, sorry, root 5 squared is 5. I'm going to cancel this 5 with the 3, so I get 400 pi over 3. Now what would that be measured in? We are measuring in seconds, so time is in seconds, and the distances were in meters. So there we go. dx by dt is 400 pi over 3.